actually research this stuff. It's cool. At any rate, he did a postdoc at the other UW. How many of you ever searched UW and found University of Wisconsin? Yeah, all right, yeah. Happened to me today. You know, it's like, not that UW, At any rate, but he's here to ask the really important question. Does the poo come from you or something that goes moo? Take it away.
Thanks. So yeah, I have this really scientific title here, and basically the idea is if we have an issue in the water, like bacterial pollution, we're interested in who's it coming from? Is it coming from you, or is it coming from cows, things that say moo, etc.? And we're trying to do this in the context of this program, SoundCitizen. Some of you may be familiar with it, others maybe not. Basically, this is a citizen science network of people. I'm in the scientist end here, well, wherever I am, up there. And we're interested in collecting samples of water, shipping them off to the lab, where I am, and trying to determine how our human activities impact the water quality in the Puget Sound. We also have all these other program goals. I'm more on the scientist end, so I'm going to concentrate on this one right here, which is to make a rigorous contribution to the scientific knowledge about human impacts. And we're going to do this, or part of the goal of the program after it's moved to the Center for Urban Waters from University of Washington, Seattle, is through something called source apportionment. Source apportionment is kind of a mouthful of a term, and the general idea is that we're trying to determine what the different effects of different sources are. Hopefully we can have tracers of each individual source, and through measurement of those tracers we can determine the impacts of each source on a water quality parameter of interest. In the case of the poo, this would be bacteria. So I mentioned that we're going to be using tracer chemicals to trace particular sources. So one question might be, how do we measure these tracer chemicals? It's kind of a multi-step process. The first step here, let me see if I can get this. There we go. So the first thing we need to do is collect a water sample. In this case, we've got our star undergrad here, Derek Overman, collecting a water sample, but this is where the citizen science component usually comes in. A citizen volunteer can collect a 1 liter water sample, mail it to us, and we can do our fairly sophisticated lab work on the sample from there. So here Derek is collecting a water sample. He then ships it off to the lab where the sample is filtered to get all the gunk out of it. We then pull the tracer chemicals out of the water and stick it onto this little solid phase cartridge here, and then get all the chemicals off of that cartridge into a little vial. The basic point here is that we're taking 1 liter of water here, 1,000 milliliters, and concentrating all those chemicals into 1 milliliter. So that's a factor of 1,000 concentration. The reason we do that is that in the water there, or in the water out there, these chemicals are usually present at parts per trillion levels, not very much. We can concentrate them into parts per billion levels, still not very much, but when you have one of these fancy piece of instruments there, a mass spectrometer, that's a lot. So once we've got it there, then we can do our laboratory work and determine the exact concentration of the tracer chemicals we're interested in. So back to this mouthful of a term, source apportionment. We could talk about this in terms of what are the tracers for runoff from a cow pasture or street runoff, but I've got this hopefully illustrative example of what if you had a mixture of liquids that you might find in your kitchen. If we measured the tracers in those liquids, we might find that milk has a high concentration of lactose but not much vitamin C or fructose. We might find that cola has more sugar and not much vitamin C or lactose. Orange juice might have vitamin C and a little bit of sugar. So those would be what we call the source profiles of each of those individual liquids. Okay? So then if we had a mixture, we would assume that that mixture is made up of little bits of each of the individual liquids. And so if we measured the tracers, and we've got our profiles here, we can do a statistical analysis on that mixture using the concentrations of the tracers, and hopefully we can determine that the mixture is 34% milk, 26% cola, and 40% orange juice. Also, we've got our uncertainties here, right, because it's about 34%. So, With that as a background, I've got some data from a World Oceans Day sampling, that we did in June of 2012. I just want to point out that on the y-axis, this is fraction detected, not concentration. Okay, so this is the number of hits that we're getting out of total number of samples, and these are our tracers here on the x-axis. This is the total Puget Sound. This is North Puget Sound, Central Puget Sound, South Puget Sound. What I also want to sort of focus here is a few of these chemicals I'd like to, or we're thinking that we can use as specific tracers. So atrazine is an herbicide. We're thinking that that can be used as a tracer of runoff. Okay, paraxanthine is a human metabolite of caffeine. That would be a tracer of wastewater. And carbamazepine is a anti-seizure medication that's not removed by wastewater treatment processes. And so, whereas paraxanthine is removed quite efficiently by wastewater treatment, the idea here is that we could differentiate between septic tanks and wastewater treatments with these two things. I'm going to talk over the music a little bit to thank some people here, our citizen volunteers, and particularly Derek, Jessica, and Connor. I get to talk about it, but they do all the real work. So thanks a lot.
Thank you very much, Justin.